Hi, good morning, everyone. Thanks for coming to listen to my talk. Today, I'm going to talk about my work measuring the disk masses with CO isotopologues. I hope you can hear me well. So I'm a grad student here at the University of Arizona, and my advisor is Ilaria Pascucci, who sits here. And this work is a collaboration with also Uma Gorty and Maxim Rurod from NASA Ames and SETI Institute. And so part of my work will also be included with the ALMA large program HPRO. So it's also a collaborative work by all of awesome collaborators around the world. So as Christine and also you heard about the protoplanetary disks, they basically form from the molecular cloud, and we believe they should be the location where the planets are formed. And as a spoiler alert, so basically what we find for the protoplanetary disks is we find a large protoplanetary disk masses compared to the literature values, and we also did not find a significant CO depletion. And here I'm going to introduce our work. Sorry. Seems not really advancing. Guess I'm helping. Okay. Great, thank you. So as I already described, the disk masses are basically the total amount of the solids and volatiles that are available for the forming planets. And here we mostly care about the volatiles because as they form from the interstellar median, we believe the gas-to mass ratio should be from 100. So for those very young disks, like all these disks in Looper star forming region, which is about 1 mega years or even younger, we believe they should have a relatively large gas-to-space ratio. However, in the earlier works, such as this one by Miotello et al. 2017, you can see that the gas-to mass ratio for those very young disks are actually very small. And especially for those brightest and largest disks, which is on the right-hand side of this plot, their gas-to mass ratio on the lower panel is even below 1. So that's shocking results. And we also believe from other tracers, such as the HD, as also Christine mentioned earlier, that we can observe from the far infrared. Although we don't have those facilities to observe the HD on the protoplanetary disk now, but in the past, on the few disks we already observed, we actually find a relatively large gas masses compared to the CO-based mass. Therefore, people believe it is actually the CO is more depleted, which means the previous thermochemical disk models might have the difficulties to correctly reproduce the gas masses and infer what is the correct mass budget for the forming planets. And therefore, we introduce our method, which is called DiskMint, the disk model for individual targets, and it's an open source tool that is now public on GitHub, and you can scan this QR code to get access there. It has all the self-consistent modeling methods we need to correctly model the CO isotopologues in protoplanetary disks. It includes the CO selective photodissociation on the disk surface and include the green surface chemistry, which the main reaction is converting the CO ice to the CO2 ice. And we also have the self-consistent vertical structure to correctly connect the disk surface to the disk midplane, because we're observing the CO isotopologue emission on the surface, while most of the masses and most of the activities for the forming planets should be in the disk midplane. And here I'm showing you the application on the large disk around IM Loopy, which actually is the largest disk in the Looper star forming region so far. However, from the literature, people find very low gas-to-gas mass ratio together with these very low gas masses that is only about 1. And it's hard to believe that just within 1 mega years, all the gas just magically dispersed. And otherwise, they have to include a very large CO depletion factor to get a more reasonable gas mass. And this is the beautiful ALMA images we can collect from the literature on this beautiful IM Loopy disk, ranging from 12 CO to optically thin C80, as well as this beautiful dust continuum map. And in our framework, we self-consistently model the gas and dust together in this DiskMint model. So we basically start with an input parameter that is as simple as just the stellar parameters and the size of the disk, as well as what the surface densities of the dust and gas. And then we run the self-consistent model to solve the vertical hydrostatic equilibrium. And then we run RedMC3D, which is another fantastic optically radiator transfer tool that is open source. And then we first feed the SED and as well as the dust continue to derive the surface density of the dust. And then we care about the gas, which we run our chemical network and then run another radiative transfer tool called LIME using the non-LTE mode to correctly trace the outer radius of the gas emission. And then we fit both the spectrum as well as the radio profile of this C18O optically thin gas. Therefore, we could infer both gas mass, dust mass, and the surface density of both. And we perfectly fit on the observations, which in black in this plot, with our models, which is shown in blue. And here is our result. So from left to right, it's basically the comparisons of the gas mass estimates from the literature to our recent work. Our models indicates this. Without any CO depletion, we could recover a gas mass that is nearly 2 orders of magnitude larger than the previous estimates from the thermochemical disk models. So from the left, we first have 100 times the dust mass. So basically just use the information from the continuum. And then we have the dynamical estimates because the IM loopy disk is large and massive enough to measure them through the self-gravitation terms. And then we have all the estimates from different thermochemical disk models from the earlier work by Zhang et al. 2021 to more recent works by our group, both including the Tremont et al. 2025, as well as our models. And as you can see, they have to include a very high CO depletion factor in the earliest models, or at least a factor of few, to go back to the reliable gas masses. While in our model, we self-consistently model everything related to the CO in the disks, and we recovered a gas mass that is consistent with the literature, as well as especially on the dynamical disk masses, which we believe our model is reliably tracing the CO-based gas masses. And we not only applied this our model on the IM loopy disk, but also on this large highest crater in the called RU loopy in the looped star forming region. It has the highest accretion rate, which means it should be one of the youngest in the looped star forming region. While in the literature, it also has small gas mass ratio that is only about a few. As you can see here, the trend marks the gas mass ratio from 5 to 100, while the earlier results by Miatello et al. 2017, as shown in this green region, basically suggests it only has a gas mass ratio of 3 or ish. And this means finds a relatively large gas mass that is about a factor of 10 larger with a large gas mass ratio. And we also apply our tool on the disks in the H-Pro collaborations. And if you stay here for the next talk, Ilaria is going to talk about more about the fantastic results that is bring up by the H-Pro large program. And here I'm just summarizing the findings related to the gas masses. So here are the 10 disks in the looped star forming region, which should be a representative to 1 to 2 mega years old disks in an H-Pro sample. And as you can see, compared to the earlier model point that is derived in Miatello et al. 2017, either using a combination of the CO isotopologue and NTH plus, or using our more self-consistent modeling framework, both of us find consistent results, and it's about a factor of 10 to 100 larger for many of those large disks. Therefore, actually the gas mass of the protoplanetary disks are not that as depleted as many people thought in the literature. And we actually find many of those, especially those bright and large disks, should have comparable gas masses to our solar system, as their mass should be close or even larger than the minimum mass solar nebula. So it's not that hard to form a planetary system that is like our own. And as a bonus, I'm going to show you this plot comparing the C18O flux versus the NTH plus. The NTH plus could help us to trace where is the CO snow line, which also could help us constrain what is the CO abundances on the emitting surface. And in the literature, before H-Pro, we only have a few points, and people couldn't really understand what is going on for the CO abundances. Well, as you can see here, for the disks both in loopers and the upper skull star forming regions, I'm showing you 2 arrows. The green arrow is demonstrating and actually follows what we find for the observations, that most of the disks should share similar CO abundances, while their most difference should be just the gas masses, without implementing any other CO depletion factors, like we use in our disk mean model. Our self-consistent approach should be able to reliably trace the gas masses with the CO isotopologues. And in the end, I'm going to show you this summary slide because I'm out of time, so I'm not going to just speak up every conclusion here. But please feel free to use our DiskMin tool. It's open source, and I believe it should be easy to use. And if you want to have more discussions about all the details of this and want to have more collaborations in the future, feel free to contact us. And I'm also on the final year of my PhD, so if you have other job offers, please also contact me. Thank you.
Thank you, Dingshan, for your very interesting talk. Now we're opening up for questions. Any questions?
I'm very impressed with your model. There are there's a lot of physics, which presumably has a lot of free parameters, and you're fitting to, I think, a few observational parameters. Could you say a little bit about any degeneracies that are interesting in the results that you find?
Oh, yes. So it's basically a question about any degeneracies in our model. So in our model, we basically try to minimize the input parameters and the variables we could input there, and most of them are self-consistently modeled. So the most degeneracies I could imagine is actually from the dust side, because we have not much information or understanding on what is the true opacities or dust compositions. So in our model, because we have the grain surface chemistry, so the number density of the dust grains are also important. And because we are modeling through the SED as well as the continuous flux densities, so we still need some assumptions on what is the correct kappa for the dust. And here we are assuming that they are still the interstellar median-like, so just that classical Weingarten and Drain dust grains from the interstellar median. And of course, if we believe it's more comet-like our solar system, then the kappa would have about a factor of 10 difference. And then that would result in a difference of nearly an order of magnitude different on the dust masses. However, we also tested it in our recent work, and you can check the latest work that we just put out last week. And even though if we change the dust opacities, the final result we got for the gas masses would not be significantly affected because the tracers we are using is optically thin. So they are not that dependent on the thermal structures of the disks. I hope that answered your question.
Okay. Any other questions?
Hi, thank you for thank you for your talk. Maybe you said this and I missed it, or Larry's going to say it, so I apologize if it's already been covered. But for what kind of gas, let's see, like disk masses down to what lower limit is this a good diagnostic for the gas mass? Like, is this going to be appropriate for disks that are forming around stars that will become M-dwarf stars, or kind of what's the lower stellar mass limit?
Oh, yeah, we actually are building a grid that is covering all the disks around all different stellar types. I would say the stellar mass, that's the lowest we can, covered in our grid is 0.1 solar masses. So I believe it's low enough to cover most of the disks around all different kinds of stellar types. And the only thing that we require is it's an optically thin tracer that is from the CL isotopologues. And for most of the massive and large disks, we prefer the 18O, but for tiny disk that's it's like for example, the debris disks that people are observing, even the 13CO or the 12CO might become optically thin. And by using those optically thin tracers, we believe we could also retrieve a relatively good gas mass estimates.
Okay, thank you. Let's thank Dingshan again.